In this video, we shall be giving a proof of correctness of the Floyd-Warshall algorithm. Now, the algorithm starts by inputting the direct distances matrix A, which is the direct distance from each of the nodes I, represented by the rows, to each of the columns J. So, in this algorithm, we proceed iteratively on P. So, at first, we consider P equal to 1. Now, for each of the rows I, we consider for I not equal to P. So here we need I equal to 2 because P equals 1. We then consider for each of the columns J, the distance to 1, because I is 2, P is 1, plus 1 for the P, J. Consider whether this is indeed less than delta 2J. So in doing this, we are looking along this row. Now, the delta 2, 1 is given by this entry. What we are in fact doing is comparing this entry, adding it to each of these to see whether it is less than this value over here. We continue along each of the J's. So in essence, if you consider the graph, we actually are considering each of the nodes I, so here I equals 1, sorry 2, I equals 2. Considering travelling along to node P, which here equals 1, and whether this diversion travelling to each of the J's is in fact quicker than the direct distance here from each of the I's to each of the J's. And if so, we update the direct distances matrix to reflect this. Now we proceed by induction on P. So suppose we want to find the shortest distance from I to J, and we found in the P-1 iteration that travelling via node P-1 was indeed quicker. Then we would define delta ij to have been delta I P-1 plus delta P-1 J. So now in the next iteration, the pth iteration, we consider the distance from I to J traversing along node P, and then from P along the shortest distances from P to J. Now, if indeed travelling via this new node P is shorter than the delta ij which we've defined up here, then we would update the direct distances matrix to reflect this. And so along each iteration we would always have the shortest distance. So now suppose we already have the shortest distance matrix. However, unfortunately, we have for some 3 nodes that we have a negative cycle. So consider this diagraph. Now consider the path 1 to 2 to 3, then back to 1 is less than 0. Then we would forever be stuck in this continual loop because the Floyd-Warshall algorithm constantly wishes to minimize the distance travelled. And when this is negative, it will keep going through this loop. Now this is particularly a problem when considering going from node 1 to node 4 over here, because we will keep going along this infinite loop because this keeps minimizing our distance, and so we won't ever actually reach node 4. Hence, having the Floyd-Warshall algorithm terminate if any indication of a negative cycle exists is crucial to the algorithm being a success.